Look up tonight, if you can. Find the darkest patch of sky you're able to reach, the place where your eyes have to work to find anything at all. Hold your gaze there, not at a star, between the stars. In the space that seems at first like pure nothing. Now consider this. If you were to take a photograph of that nothing a long exposure, hours of light gathering, the way the great telescopes do, you would find it isn't nothing at all. You would find galaxies, thousands of them, tens of thousands, each one containing hundreds of billions of stars, each one separated from the next by distances so vast they make the word vast feel almost embarrassing to use. The universe is not empty, it is almost incomprehensibly full, and for a very long time, we thought we understood in broad strokes, at least how it got that way. We had a story, a clean, logical, satisfying story, about how the cosmos organized itself, about how order emerged from the hot, formless aftermath of the Big Bang, about how gas clouds collapsed into the first stars, and those stars lived and died and seeded the universe with heavier elements. And over millions of years, gravity gathered those elements into larger and larger structures, until finally galaxies formed. Great spinning collections of matter, pulling themselves together across cosmic time. And at the center of each of those galaxies, something waited, a darkness heavier than anything else in the universe. A point of such extreme gravity that not even light could escape it. Supermassive, black hole, millions of times the mass of our sun, sometimes billions of times, sitting at the very heart of the galaxy, like a seed that had grown into something terrible and magnificent. That was the story. Galaxies first, black holes second. Stars live and die. Their heaviest remnants sink toward the galactic center. They merge and grow over billions of years. And slowly, patiently, a monster accumulates. It made sense. It fit the math. It fit the observations we had. It fit the way we understood gravity and time and the slow machinery of cosmic evolution. There was just one problem. Was wrong. Not entirely wrong. The universe is rarely so clean as to be entirely wrong about anything, but the picture, the sequence, the order, the assumed direction of cause and effect, that picture had a crack running through it that we simply hadn't seen yet, because we hadn't looked far enough, we hadn't looked early enough to understand what JWST found. When it finally did look, when it turned its golden mirrors toward the very edge of what is visible, toward light that has been traveling since the universe was barely a fraction of its current age, you first need to feel the weight of what we thought we knew. Think of it this way. Our Milky Way galaxy is roughly 13.6 billion years old. It contains somewhere between 100 and 400 billion stars, and at its very center, 26,000 light-years from Earth, sits a black hole called Sagittarius, weighing in at about 4 million solar masses. By galactic standards, that is actually modest. Some galaxies harbor black holes billions of times more massive than our Sun. The ratio matters here. Across the universe, in galaxy after galaxy after galaxy, that astronomers have measured, a pattern holds. The mass of the central black hole is consistently about 0.1% of the total mass of the galaxy's central bulge of stars. Not exactly, not in every case, but as a rule that holds with remarkable consistency across cosmic time. 1 to 1,000. Black hole to stellar mass. A ratio so persistent that it doesn't look like coincidence. It looks like the two things, galaxy and black hole, are somehow linked, somehow growing together, regulated by the same forces, speaking to each other across scales we can barely imagine. This relationship has a name in astronomy. It is called the M-sigma relation, the correlation between a black hole's mass and the velocity dispersion of the stars around it, and it strongly implies a kind of cosmic co-evolution. Galaxies and their central black holes growing up together, constraining each other, feeding each other, checking each other's growth in a long, slow cosmic dialogue, stretching across billions of years. It was beautiful, as cosmological models go, self-regulating, elegant. And then the James Webb Space Telescope was pointed at the early universe. Let yourself settle into this moment for a second. Feel the weight of your body against whatever is beneath you. Let your breathing slow. The universe is very old, and it has been doing what it does for a very long time without needing anything from us. You are just here to listen, to let the story move through you. Because what happens next, what JWST saw when it finally looked backward far enough, is not a small revision to our understanding. It is not a footnote. It is the kind of finding that makes physicists sit very quietly for a moment before reaching for a pen. The black holes were already there. Not just there, they were enormous, supermassive. Billions of solar masses packed into regions smaller than our solar system. And the universe around them? Young, so heartbreakingly young. The light JWST collected had been traveling for more than 13 billion years before it landed on those golden mirrors. These black holes existed when the universe was only a few 100 million years old, before most of the stars had formed, before most of the galaxies had assembled. They were there first, or at least that is what the data seems to be saying. And when the data from a telescope this powerful says something this surprising, the scientific community does not immediately announce a revolution. It asks harder questions, it runs more observations, it looks for errors, but the errors are not showing up. The pattern keeps emerging. Black holes in the early universe that are far too massive, far too early, by every model we have. The ratio of black hole mass to stellar mass, that familiar 1 to 1,000, is inverted in these early systems. Not 1 to 1,000, closer to 1 to 1, or sometimes, impossibly, the black hole appears to outweigh the stars entirely. A black hole sitting at the center of a galaxy that barely exists yet, an engine running before the machine around it has been built. For a long time we thought galaxies made black holes. Now we have to ask whether black holes made galaxies. And that question, quiet and enormous and patient as the darkness between stars, is what we are going to spend tonight with. Let it settle. Let it dissolve into the slower rhythms of your breathing, the cooling of the room around you, the particular silence of very late or very early hours. The universe had a secret, a very old one. We are only now beginning to hear it. There is a particular kind of darkness that exists only in space. Not the darkness of a room with the lights off, not the darkness of a forest at midnight. Something older than that, something that has never known light at all, except for the light that passes through it. Ancient and stretched, on its way from somewhere impossibly far to somewhere it was never supposed to reach. For most of human history, we looked at that darkness with nothing but our eyes, and our eyes, as remarkable as they are, can only see so far. Then we built lenses, then mirrors, then we learned to capture light on glass plates, then film, then digital sensors sensitive enough to catch a single photon that has been traveling since before the Earth existed. Each generation of instrument pushed the boundary a little further. Each one revealed that the universe was larger, older, stranger than the one before it had shown us. But there was always a wall, a horizon beyond which even our best instruments could not see clearly. The early universe, the first few 100 million years after the Big Bang, sat behind that wall like a rumor. We knew it was there. We could infer things about it, but we could not see it. Not clearly, not with the kind of detail that turns inference into knowledge. Then, on the morning of December 25, 2021, a rocket lifted off from a launch pad in the Guyana Space Center on the northeastern coast of South America. On top of that rocket sat a telescope, folded into itself like an origami flower, packed into a cylinder with the kind of care usually reserved for the most fragile things in the world, which in a sense it was. The James Webb Space Telescope had taken 30 years to build. It had cost $10 billion. It had involved the work of thousands of engineers, scientists, and technicians across 20 countries. It had been delayed so many times that some of the astronomers who originally proposed it had retired before it ever launched. And on Christmas morning, it rose, slowly at first, then faster, then gone a bright point, disappearing into the blue above the Atlantic Ocean, leaving behind only a contrail and a silence full of 30 years of held breath. Over the following weeks, the telescope unfolded itself in space. A sunshield the size of a tennis court, 5 layers of material thinner than a human hair, designed to keep one side of the telescope at nearly -233 degrees Celsius, cold enough that the infrared light from the distant universe would not be drowned out by the warmth of the instrument itself. 18 hexagonal gold-coated mirrors, each one machined to a precision measured in nanometers, locked themselves into a single surface 6.5 meters across. It took months. Every step carefully choreographed, every mechanism tested against the possibility of a single point of failure that could end everything. There were 344 single points of failure on the James Webb Space Telescope. Every one of them worked. By the summer of 2022, the telescope was in position 1 million miles from Earth, orbiting a gravitational balance point called Lagrange Point 2, where the pull of the Sun and Earth cancel each other out, and a spacecraft can hover in a kind of permanent stillness. And then it opened its eyes. The first images were released to the public on July 12, 2022. In a patch of sky no larger than a grain of sand held at arm's length, there were thousands of galaxies. Some of them sharp and bright, some of them stretched into arcs by the gravity of objects between them and us, a phenomenon called gravitational lensing, where the fabric of space-time itself bends light around massive objects, the way a glass lens bends light in your hand. Some of those galaxies were so far away that the light reaching JWST had left them when the universe was less than 1 billion years old. People cried, cough. Scientists who had spent their careers waiting for this instrument sat in conference rooms and felt something that is hard to name, something between awe and relief, and the particular vertigo of realizing that the thing you have been waiting for is finally actually here. But the images were not the revelation. The images were the beginning. Because what Webb was built to do, what made it different from every telescope before, it was not just take beautiful pictures, it was to see in infrared. Visible light covers a narrow slice of the electromagnetic spectrum. The universe, however, communicates in a much wider language, and crucially, the most distant objects in the universe have had their light stretched by the expansion of space itself. When a galaxy is so far away that the universe has been expanding for 13 billion years between us and it, the light it emits, originally ultraviolet or visible, has been redshifted all the way into the infrared, made invisible to our eyes, made invisible to Hubble, made visible, finally, to Webb. This is why the early universe sat behind a wall for so long. We were looking for it with the wrong kind of eyes. Webb was built with the right kind. And so, when astronomers began processing the first deep field data, sorting through galaxies by their redshift, by how far their light had traveled, by how young the universe was, when that light first began its journey, they found something they had not expected. Not in the first months, not all at once, but gradually, with the slow accumulation that real science usually moves in, the pattern emerged that nobody had a clean explanation for. The early universe was not behaving the way it was supposed to. There were galaxies where there shouldn't be galaxies yet, bright ones, massive ones. Galaxies that looked in some ways more developed than they had any right to be, given how little time had passed since the Big Bang. And at the center of some of them, hinted at first, then confirmed again and again in object after object, black holes, enormous ones. Ones that, by every model we had built over decades of careful observation, simply should not exist yet. Astronomers have a phrase they use when the data disagrees with the model in a way that can't be easily dismissed. They say, "This is not expected." It is, in the careful language of science, about as close to astonishment as the literature allows. In 2022 and 2023, paper after paper began appearing in the journals with some version of that phrase. The early universe was not expected to look like this. These black holes were not expected to be here. Not yet, not this big, and if they were here, if they were real, and the data kept insisting, they were, then something about the story we told about how the universe organized itself was going to have to change. Let that thought rest gently somewhere in you as you sink a little deeper into wherever you are right now. You don't have to solve it. Nobody has solved it yet. That is what makes it beautiful. The universe opened a door that we didn't know was there, and on the other side of it was not an answer. It was a better question. Which came first, the galaxy or the darkness at its heart? Imagine you are an archaeologist, not digging through soil and rock, but through light, through time. Every layer you go deeper is not a stratum of Earth, it is 1 billion years further back, 1 billion years younger, 1 billion years closer to the moment when everything began. And as you dig, you expect to find less complexity, less structure, less mass gathered into coherent forms, because structure takes time. Gravity is patient, but it is not instant. Gas clouds don't collapse overnight. Stars don't form in an afternoon. Galaxies don't assemble themselves in the cosmic equivalent of a weekend. The early universe, by all our models, should look like a rough draft. Sparse, unfinished, full of potential but short on execution. That is what we expected to find when Webb looked backward into the first billion years. That is not what it found. What it found instead was something that confused almost everyone who looked at it carefully. Galaxies that were too bright, too massive, too structured, not rough drafts, finished things, or nearly finished, sitting in a universe that shouldn't have had time to finish them yet. One early paper described it plainly. JWST is finding too many galaxies, too massive too early, not one or two anomalies, not a handful of outliers that could be explained away by measurement error or unusual local conditions, a population, a consistent, repeating pattern of objects that exceed what our best simulations predicted should exist in the first few 100 million years after the Big Bang. The models weren't off by a little. In some cases, they were off by orders of magnitude. Now pause here for a moment. Science is full of measurements that turn out to be wrong. Instruments can be miscalibrated. Assumptions can be baked into an analysis in ways that take years to notice. The early data from a new telescope always requires careful handling. Systematic errors hide in new instruments, the way dust hides in corners you haven't looked at yet. Astronomers knew this. They looked for the errors. They looked very hard. And what they found, what keeps emerging as the data accumulates and the methods improve, is that the galaxies are real. The masses are real. The redshifts are real. The early universe is doing something that the models didn't predict, and the models are going to have to learn to account for it. But the galaxies, surprising as they were, turned out not to be the deepest part of the surprise. Because sitting at the centers of some of them, embedded in these two massive structures, were black holes, and the black holes were the part that truly didn't fit. Here is why, in the universe we live in today, the mature, 13.8 billion-year-old universe, we have spent centuries studying the relationship between a galaxy and its central black hole, follows a pattern, 1 to 1,000, 1 part black hole for every 1,000 parts of stellar mass. A ratio that holds across an enormous range of galaxy sizes, dwarf galaxies and giant ellipticals, isolated galaxies and galaxies in clusters, galaxies actively forming stars and galaxies that stopped forming stars billions of years ago. The ratio persists, which tells us something profound, that whatever process governs the growth of a central black hole is deeply connected to whatever process governs the growth of the galaxy around it. They are not independent. They regulate each other now. When JWST observed black holes in the early universe, black holes from when the universe was only 500 or 600 million years old, it measured their masses, and it measured the stellar masses of the galaxies around them. And the ratio was wrong. Not wrong in a subtle, technical sense. Wrong in a way that made people check their instruments and then check them again. Instead of 1 to 1,000, some of these early systems showed ratios closer to 1 to 10, or 1 to 1. Or in the most extreme cases, the black hole appeared to be more massive than all the stars in the galaxy combined. An overmassive black hole, that is the term astronomers settled on. Overmassive, as though the black hole had gotten ahead of itself, as though it had grown without waiting for permission, without waiting for the galaxy around it to catch up. One system observed in 2025 contained a black hole with a mass nearly equal to the total stellar mass of its host galaxy when the universe was only 570 million years old. For context, our Sun is one star among perhaps 300 billion in the Milky Way. At the center of our galaxy, the black hole is about 4 million solar masses. Our galaxy has a stellar mass roughly 50 billion times that of the Sun. Our black hole is, by cosmic standards, appropriately sized. It knows its place. These early black holes did not know their place. Or perhaps more accurately, perhaps they did know their place. Perhaps their place was simply not where we expected it to be. Perhaps they were not running ahead of the galaxy. Perhaps they were running before the galaxy. Perhaps the galaxy was the thing that came second. This possibility that black holes preceded galaxies, that the darkness at the heart of every star system was not a product of those stars, but their cause began to be taken seriously, not as a fringe idea, but as a genuine scientific hypothesis worthy of investigation. And the more JWST looked, the more the data seemed to lean toward it. Not conclusively. Science moves carefully, but directionally, persistently, the way a river moves, not in a straight line, not without resistance, but always, ultimately, in the same direction, downhill, toward the lowest point, toward the truth of the thing. There is something quietly unsettling about this possibility, if you let it sit with you. We have always imagined galaxies as the primary structures of the universe, the great cathedrals of matter, billions of stars arranged by gravity into spirals and ellipses, glowing with the accumulated light of nuclear fires burning at their hearts, and at the center of each cathedral, almost like an afterthought, almost like a consequence, a black hole, a remnant, a leftover, a byproduct. But what if we had the relationship backwards? What if the black hole is not the afterthought? What if the galaxy is? What if all those billions of stars, all that light, all that warmth, all that complexity is simply the debris that accumulated around something far older and far darker than any of it? What if the cathedral was built around the void at its center, not the other way around? Let that thought move through you slowly. There is no rush. The universe has been sitting with this question for 13 billion years. You have all night, Dove. And what we need now, what the data demands, is not just a new measurement, it is a new theory. Or perhaps several competing theories, each one trying to explain how a black hole becomes enormous before the stars around it have had time to be born. But before we get to the theories, we need to meet the strangest objects the James Webb Space Telescope has ever found. Small, ancient, impossibly red, scattered across the early universe like embers from a fire that no one remembers starting. Astronomers call them little red dots, and they may be the key to everything. There is a particular kind of discovery in science that doesn't arrive with fanfare. It doesn't come as a single dramatic moment, a gasp in the control room, a phone call at midnight, press conference with the president standing at a podium. It comes quietly, almost accidentally, as a category of thing that keeps showing up in the data, again and again, that nobody has a name for yet. In the first deep survey images from the James Webb Space Telescope, astronomers noticed them almost immediately. Small objects, compact, unresolved meaning. They were so distant and so concentrated that the telescope couldn't distinguish any internal structure. Just a point of light, a dot, and they were red. Not the soft rose of a stellar nursery, not the warm amber of an aging star. Something deeper than that, a red that sits at the very edge of the infrared, the color of things that are either very old, very dusty, or very far away, and in some cases, all three at once. They appeared at high redshift, meaning their light had been stretched enormously by the expansion of the universe. Meaning, they were being observed from an era when the cosmos was between 600 million and 1 billion years old, sometimes even younger than that. And there were a lot of them. More than 300, confirmed by the time astronomers started taking them seriously as a category. Hundreds more candidates waiting for spectroscopic confirmation, scattered across different deep field observations, showing up in data from different instruments, different teams, different methodologies. Too many to be flukes, too consistent to be noise. Astronomers gave them a name, the way astronomers often name things they don't yet understand with a description that is accurate but says almost nothing about what they actually are. Little red dots. The name has stuck, and the debate about what they actually are has not stopped since. The first hypothesis was straightforward. These are compact galaxies, very early, very dense collections of stars, packed tightly enough that their combined light appears point-like from our vantage point across 13 billion years of space. They are red because they are full of dust, and dust absorbs shorter wavelengths and re-emits them in the infrared. They are bright because they are forming stars at an extraordinary rate, a burst of stellar birth that saturates the surrounding medium with energy. It was a reasonable hypothesis. It explained some things, but not everything. Because when astronomers began taking spectra of these objects, breaking their light apart into its component wavelengths, the way a prism breaks sunlight into a rainbow, something unexpected appeared: broad emission lines. Specifically, broad lines from hydrogen, the kind of spectral signature you get when gas is moving very, very fast, not the speeds you'd expect from stars orbiting inside a galaxy. Speeds that implied something was accelerating material to a significant fraction of the speed of light. That is, what happens near a black hole. Gas falling toward a supermassive black hole gets caught in the gravitational field, heated to millions of degrees and flung outward in winds that travel at enormous velocities. Those velocities broaden the spectral lines, smear them out in a way that is unmistakable once you know what you're looking for. About 80% of little red dots, when their spectra were examined carefully, showed these broad lines. 80%, that is not a contamination, that is a signal, which meant that most of these compact, ancient, deeply red objects were not simply dense early galaxies. They were something more or something different. They had active black holes at their centers. Black holes that were feeding, growing, radiating energy. But then another measurement came back, and it added a layer of strangeness that no one had quite anticipated. The stellar masses didn't match. When astronomers tried to estimate how many stars were inside these little red dots, using the brightness of the light, the shape of the spectrum, everything in the standard toolkit, the numbers came out inconsistently. Sometimes the stellar mass seemed extremely high, implying an enormous population of stars crammed into a tiny space. Sometimes it seemed almost non-existent. Sometimes the models couldn't settle on an answer at all, and gave wildly different results depending on which assumptions you fed into them. And in some cases, in some of the most extreme, most studied, most carefully observed little red dots, the answer that kept coming back was something close to zero. Almost no stars, almost no galaxy. Just a black hole, sitting in a cloud of gas, glowing. There is a particular quality to that image, if you let it form fully in your mind. Not a black hole at the center of something. Not a black hole embedded in a structure, surrounded by stars and dust lanes and spiral arms and all the familiar furniture of a galaxy. Just a black hole, alone in the early universe, gathering matter and radiating light, existing in a time before the architecture of the cosmos had been fully assembled around it, before the neighborhood had been built, before most of the stars in that region of space had even formed. One of the most striking examples has a name, or rather, a catalog designation. The way things discovered by telescopes tend to be named. It is called A2744QSO1. It sits behind a galaxy cluster called Abell 2744, whose gravity acts as a natural magnifying glass, bending and amplifying the light of more distant objects behind it. Through that gravitational lens, JWST detected A274SO1, the black hole, with a mass of approximately 40 million times the mass of our Sun, existing when the universe was roughly 700 million years old, with gas around it, and almost no stars. 40 million solar masses, no galaxy to speak of, just the darkness and the light it makes as it consumes. When the team that studied this object published their findings, one of the researchers described it as a remarkable finding, a black hole that appeared to have formed prior to, and independent of, the stars within what would eventually become its host galaxy. Prior to, independent of, those two phrases sit at the center of everything we are trying to understand tonight. Because if A2744QSO1 is what it appears to be, if the little red dots are what they appear to be, then the story of how structure formed in the early universe needs to be rewritten from very close to the beginning. Not edited, not revised, rewritten, and that rewriting depends entirely on a question that no one has yet answered with certainty. How does a black hole that massive exist that early? Where did it come from? How did it grow so large so fast, in a universe that was barely old enough to have a first generation of stars? There are three answers being seriously considered right now by the people who spend their lives thinking about this. Three different stories about the origin of darkness, each one stranger than the one before it, each one reaching back toward the very first moments of time in a different way. Let your eyes close a little more. Let the room settle around you. There is no urgency here. The little red dots have been waiting 13 billion years to be understood. They can wait a little longer, and so can we. There is a specific moment in any investigation, scientific or otherwise, when a hypothesis stops being a hypothesis, when it stops being the thing you suspect might be true, and becomes the thing you have actually seen. That moment, in the story of black holes and galaxies, has a name. It has a catalog number, technically. But the name that matters, the description that captures what it actually is simpler than any alphanumeric designation. It is a black hole with no galaxy. Not a black hole at the center of a very small galaxy. Not a black hole in a galaxy so faint that the instruments struggled to detect it. A black hole sitting in the early universe, surrounded by gas, radiating enormous amounts of energy, and with almost nothing else around it. No stellar mass to speak of, no assembled structure, no collection of stars that would qualify by any reasonable definition as a galaxy. Just the darkness and the light it makes as it feeds. To understand why this matters, why this particular object, discovered by JWST and published in the scientific literature in the last few years, changed the texture of the conversation, you need to understand what it takes for a supermassive black hole to exist at all. In the model we held before JWST, the sequence was clear. The first stars form. They are enormous by modern standards, hundreds of times the mass of our Sun, burning through their fuel in a few million years before collapsing. The very largest of them leave behind black holes. These black holes are heavy by stellar standards. Perhaps 100 solar masses, perhaps a few hundred. They are seeds, small ones. Then time does its work. The seed black hole sits at the center of a growing structure. Gas falls in. Occasionally other black holes merge with it. Slowly, over hundreds of millions of years, it grows. It feeds. It accumulates mass the way a river delta accumulates sediment, gradually, continuously, driven by the patient geometry of gravity. To reach 1 billion solar masses, by this model you need time. Not infinite time, but substantial time. The kind of time that, when you run the numbers carefully, leaves very little margin. Even accreting at the theoretical maximum rate, the Eddington limit, the point at which radiation pressure pushes outward as hard as gravity pulls inward. A seed black hole of a few hundred solar masses needs hundreds of millions of years to reach 1 billion solar masses, maybe more. and the early universe, by definition, did not have hundreds of millions of years to spare. When JWST began finding billion solar mass black holes at redshifts corresponding to 500 or 600 million years after the Big Bang, the first response from theorists was to check the math, to see if there was some way, some combination of faster accretion, earlier seeds, more efficient growth that could get you from a stellar mass black hole to a supermassive one in the time available. The math was uncomfortable. It wasn't impossible, but it was tight, uncomfortably tight, the kind of tight that suggests the model is being stretched rather than confirmed. And then came a 2744 QSTO-1. The object sits behind a galaxy cluster called a Bell 2744. The cluster itself is large enough that its combined mass, dark matter and ordinary matter together, warps the fabric of space-time around it. Light from more distant objects, passing through that warped region, gets bent and amplified. The cluster acts as a natural lens, a gravitational magnifying glass, allowing telescopes to see objects that would otherwise be too faint to detect through that lens. JWST saw a 2744 QSO-1. The measurements when they came back were striking. A black hole mass of approximately 40 million solar masses, a redshift placing it at roughly 700 million years after the Big Bang. Surrounding it gas, yes, plenty of gas, material being heated and accelerated and flung outward in the winds that active black holes generate, but almost no stars, no galaxy. In any meaningful sense, the ratio of black hole mass to stellar mass was not 1 to 1,000. It was not 1 to 1. It was inverted so completely that the usual ratio ceased to apply. There was barely enough stellar mass to register, and what little there was existed, not as a structured galaxy, but as a cloud of material that had not yet organized itself into stars in any significant way. The team that published the discovery was careful with their language, the way scientists always are. They noted the uncertainties. They acknowledged the difficulty of measuring stellar masses in objects this distant and this unusual. They did not claim to have definitively solved anything, but they also said something that is hard to walk back once you have said it. They said the black hole appeared to have formed prior to, and independent of, the stars within what would eventually become its host galaxy. Prior to, independent of, a black hole that did not emerge from stellar evolution. A black hole that was not the product of a galaxy's long internal life. A black hole that was simply there already, before the structure that would eventually surround it had assembled itself. If that is what a 2744 QSO-1 is, and the data, carefully examined, keeps pointing in that direction, then it is not an anomaly. It is a category. It is the thing we had not imagined, a black hole that precedes its own galaxy, that exists, fully formed and feeding, in a universe that has not yet built the architecture of stars and gas and dark matter halos that we associate with the word galaxy at all. And it raises a question that sounds almost philosophical but is entirely physical. If the black hole came first, if it existed before the galaxy, then what made it? Not a star collapsing, not millions of years of slow accretion from a small seed. Something else. Something faster. Something that could produce tens of millions, or hundreds of millions, or billions of solar masses in the time available. Something that we have theorized about for decades but never directly observed. Something that, in the early universe, may have been far more common than we ever suspected. The search for that something is where the science currently lives. It is an active search, the live one. Papers are being published now, not years ago, not in the comfortable past of settled knowledge, but now, this year, this month, proposing mechanisms and testing them against the data, and revising them and testing them again. 3 serious candidates have emerged. 3 different answers to the question of where a black hole goes when it has no galaxy to be born from. 3 stories about what darkness does when it is left alone in the early universe, with nothing but time and gas and the relentless pull of its own gravity. We are going to move through each of them tonight, slowly, without urgency, the way you move through something large and strange and worth understanding fully before you set it down. But first, take a moment here. Notice the quality of wherever you are right now, the temperature of the air, the small sounds that persist even in near silence. The particular weight of this hour, late as it is, with the world quieted around you. You are listening to the story of what was here before most of what exists, before the stars, before the light they made, before the long chain of nuclear chemistry that produced every atom in your body, before almost everything. Something was here, and we are only now, with a telescope made of gold and time and extraordinary human patience, beginning to see what it was. Numbers, in cosmology, are never just numbers, they are arguments. Each one is a claim about the universe, about what it contains, how it behaves, what it is capable of doing within the constraints of physics as we understand them. When a number comes back from an observation and fits neatly inside those constraints, it confirms something. When it doesn't, when it sits outside the boundary of what the models say is possible, it is not just an anomaly, it is a question. And right now, the early universe is full of numbers that are questions. The most persistent of them is a ratio. We have talked about it already, the relationship between a black hole's mass and the mass of the stars in the galaxy around it. 1 to 1,000 theory. The number that holds so consistently across so many galaxies in the modern universe that it stopped looking like a coincidence and started looking like a law. But there is something worth sitting with more carefully here. Because the 1 to 1,000 ratio is not just an observation, it carries within it an implied story about how things grew. It implies that galaxies and their central black holes were not independent of each other, that they grew together, constrained each other, communicated with each other, across scales of hundreds of thousands of light years. Through the only language, gravity, speaks the language of mass and motion and time. When a black hole grows too fast, when it accretes too much gas too quickly, the energy it releases heats the surrounding medium and pushes gas outward. It suppresses star formation. It limits its own food supply. It self-regulates. When a galaxy grows too fast, when star formation produces too many massive stars that explode as supernovae, those explosions heat and stir the gas, making it harder for more stars to form, and also making it harder for the central black hole to accrete. The galaxy self-regulates too. The result, over billions of years, is a kind of equilibrium. The feedback loop so persistent that it leaves its signature in the ratio, 1 to 1,000, not imposed from outside, arrived at slowly through the accumulated negotiations of gravity and radiation and pressure across cosmic time. That is the modern universe. That is what we see when we look at galaxies nearby, in cosmic terms, meaning within the last several billion years of cosmic history. Now look earlier. In the systems, JWST is finding at redshifts of 7, 8, 9, corresponding to times when the universe was between 600 and 800 million years old. The ratio is not 1 to 1,000. In some cases it is 1 to 100. In some cases it is 1 to 10. In the most extreme cases, objects like A2744US01, like a galaxy designated Canute Z8.6. Like a growing catalog of similar objects being identified and studied right now, the ratio approaches or exceeds 1 to 1. The black hole is as massive as the stellar population, or more massive. This is what astronomers mean when they say overmassive. They don't mean large in absolute terms, though some of these early black holes are genuinely enormous. They mean disproportionate. Out of step with what the surrounding galaxy can account for. A black hole that, given the stars around it and the feedback loops that govern co-evolution, simply should not have been able to grow this large this fast. The overmassive problem is not one problem. It is several overlapping problems, each one pointing at the same gap in our understanding from a slightly different angle. The first is the timing problem. A black hole that reaches 1 billion solar masses by 600 million years after the Big Bang had to start from somewhere. If it started as a stellar remnant, a collapsed massive star of perhaps 100 solar masses, then it had, at most, a few hundred million years to grow by a factor of 10 million, even accreting continuously at the Eddington limit. That is barely possible. And continuous Eddington limit accretion is not what we typically observe in black holes. Real black holes cycle. They feed heavily for a while, then the radiation pressure blows away their food supply. Then they quiet down. Then gas falls back in and the cycle begins again. A black hole that is cycling has less time to grow than one that is feeding continuously. Less time means the seed needs to be bigger, which brings us to the second problem. The seed problem. If the black holes we are seeing in the early universe are too massive to have grown from small stellar seeds in the time available, then either the seeds were larger to begin with, or the growth was faster than we thought, or both. Larger seeds require mechanisms we have not observed. Faster growth requires conditions we struggle to maintain in our models. Neither answer is comfortable. Both answers require the early universe to have been doing something we don't fully understand. And then there is the third problem, which is perhaps the strangest, the structural problem. In the modern universe, when we see an overmassive black hole, a black hole that is larger than the 1 to 1,000 ratio would predict, it is usually in a galaxy that shows signs of recent disruption, a merger, a collision. Something that funneled an unusual amount of gas toward the center in a short period of time and allowed the black hole to grow faster than the galaxy could keep up. Unusual circumstances, exceptional events, but in the early universe, the overmassive black holes are not exceptional. They are common. They appear in system after system after system. They appear in objects that don't show signs of major mergers. They appear in things like the little red dots, which are compact and isolated, and in some cases barely have enough stellar mass to qualify as galaxies at all. Overmassive is not the exception in the early universe. It appears to be the norm, and that changes the question entirely. If overmassive black holes are common in the early universe, if the 1 to 1,000 ratio that holds so firmly in the modern universe was simply not yet established in the first billion years, then the feedback loop we rely on to explain coevolution hadn't kicked in yet. Which means the black holes were growing without the regulation that galaxies impose on them in later epochs. Which means something else was setting the initial conditions. Something that happened before the feedback loop could establish itself, before the galaxy was massive enough to push back, before there were enough stars to heat the surrounding gas and limit the black hole's food supply. Something that allowed the black hole to grow, essentially unchecked, in the earliest moments of the universe's history. That something is what the three competing theories are trying to describe. Each one imagines a different mechanism, a different set of initial conditions, a different answer to the question of how you make something that massive that fast in a universe that is barely old enough to have cooled down from the Big Bang. And each one, in its own way, asks us to reconsider not just the sequence of events in the early universe, but what the universe fundamentally is, what it was made of, what it started with, and whether the darkness we now find at the center of every galaxy was there in some form from nearly the very beginning. Let the room hold you for a moment. Let the question breathe. 3 theories, 3 different origins for the darkness. We'll take them one at a time. Slowly, there is no hurry here. The answer, whatever it turns out to be, has been waiting 13 billion years. It will wait a little longer. Before there were galaxies, there were stars. Before there were stars, there was gas. And before there was gas, in the very first minutes after the Big Bang, when the universe was still a plasma so hot that atoms themselves could not hold together, there was hydrogen and helium and almost nothing else. No carbon, no oxygen, no iron, no silicon. None of the heavier elements that make up planets and asteroids and the bodies of living things. The universe began chemically simple, in a way that is almost impossible to fully appreciate from where we stand now, surrounded as we are by the accumulated complexity of 13.8 billion years of stellar alchemy. The first generation of stars formed from that simplicity. They are called population Ni stars, and they have never been directly observed. Not yet. They formed too early. They lived too briefly. And they died before the universe had produced enough heavier elements to make them detectable in the ways we usually detect stars. They exist, for now, as a theoretical prediction. Something the physics of the early universe demands must have happened. Even if we have not yet seen the proof, but the physics is compelling. In the absence of heavy elements, gas clouds in the early universe could not cool as efficiently as they can today. In the modern universe, when a cloud of gas starts to collapse under its own gravity, it radiates energy away primarily through the emission lines of carbon, oxygen, and other elements that act as efficient coolants. That cooling allows the cloud to fragment, to break apart into smaller pieces, to form stars of relatively modest mass, stars like our Sun, or a few times more massive than our Sun. The first gas clouds had none of those coolants. They could only radiate through hydrogen and helium, which are far less efficient. The result was that they could not fragment as easily. The pieces stayed larger. The stars that formed from them were not modest, they were enormous. Current models suggest that population C-fine stars ranged from perhaps 10 times to several hundred times the mass of our Sun. Some theoretical work suggests the upper end could reach 1,000 solar masses, objects so large that they would burn through their fuel not in billions of years like our Sun, but in a few million years. A cosmic eye blink. A massive star lives fast and dies violently. The most massive ones, above roughly 25 solar masses, end their lives not as neutron stars but as black holes. They don't explode cleanly in a supernova. They collapse. The outer layers may be ejected, or they may fall back inward, but the core becomes a black hole with a mass that is some fraction of the original stellar mass. For a population, the star of, say, 300 solar masses, the resulting black hole might be 100 solar masses. Perhaps more, depending on how much mass was lost during the star's brief life. This is the first theory for the origin of the overmassive black holes. JWST is finding the light seed scenario. The idea is that population Phi stars, these enormous metal-free, short-lived giants of the early universe, collapsed to form black holes in the first few 100 million years. Those black holes, already heavier than any stellar remnant in the modern universe, became these seeds, the starting points, the first nodes around which gas began to accumulate, around which structures began to organize, around which the long, slow process of accretion began. It is, in many ways, the most conservative of the three theories. It requires no new physics, no exotic mechanisms, no objects or processes that we have not, at least in principle, countered before. It takes things we already believe happened, the formation and death of the first massive stars, and extends them to their logical conclusion. The seeds were heavy, they grew, and given enough time and enough gas, they became the supermassive black holes we see, anchoring the earliest galaxies in the JWST data. The appeal of this theory is its elegance, its parsimony, the way it builds on what we already know without requiring a leap into the unknown. But it has a problem, the same problem that has haunted every attempt to explain the earliest, most massive black holes through conventional growth: time. Even starting with a seed of 1,000 solar masses, far larger than any confirmed stellar black hole in the modern universe, growing to 1 billion solar masses in 500 million years, requires nearly continuous accretion at or near the Eddington limit. No pauses, no quiet periods, no interruptions from the very radiation the black hole itself produces as it feeds. For most black holes, that kind of sustained growth is not what we observe. Real black holes are intermittent. They flare and quiet, feast and fast, cycle through periods of activity and dormancy. The physics of accretion disks, the swirling structures of gas and dust that feed black holes, naturally produces variability. The system is not a steady flow, it is a rhythm. To sustain Eddington limit accretion continuously for hundreds of millions of years requires conditions that are unusual at best and perhaps physically implausible at worst. Some theorists have proposed a workaround: super Eddington accretion. The Eddington limit is not, strictly speaking, an absolute wall. It is the point at which radiation pressure balances gravity in a spherically symmetric system. But real accretion is not spherically symmetric. Gas doesn't fall in evenly from all directions, it forms a disk, and in a disk, under certain conditions, gas can flow inward faster than the outgoing radiation can push it back. Super Eddington accretion, feeding that exceeds the theoretical limit, has been observed in some systems. It is real. And if the earliest black holes were super Eddington accretors, even for relatively brief periods, the math becomes much more forgiving. A smaller seed can reach a larger mass in the available time, but super Eddington accretion comes with its own complications. Cons: the measurements of black hole masses in the early universe may actually be overestimates if the accretion is super Eddington, because the standard methods for inferring black hole mass from the motion of surrounding gas assume Eddington limited accretion. If the assumption is wrong, the inferred masses may be wrong, which would help, which would make the problem less severe, but it would not eliminate it entirely. Even with generous assumptions about accretion rates and seed masses, the light seed scenario struggles with the most extreme objects. JWST has found the ones with billions of solar masses in the first few 100 million years, the ones that appear to be overmassive not just relative to their galaxies, but relative to any reasonable growth model built on stellar remnants. For those objects, a heavier seed may be required, not the collapsed remnant of a single massive star. Something larger, something that bypassed the stellar phase entirely, something that went from gas cloud directly to black hole without the intermediate step of burning hydrogen in a stellar core for a few million years first. That possibility is where the second theory lives. And it requires the early universe to have done something stranger and more dramatic than simply forming very large stars. It requires a collapse so complete, so total, so unimpeded by the usual barriers that slow the fall of matter into darkness, that an entire cloud of gas, containing perhaps 1 million times the mass of our sun, simply fell inward all at once. No stars, no supernovae, no intermediate steps, just gas, and then where the gas had been, a black hole, already enormous, already waiting, already, in some sense, ready to begin the work of building a galaxy around itself. Rest here for a moment. The first theory is the familiar one, the one that extends what we know into territory we haven't fully mapped yet. It is not wrong. It may be part of the answer for many of the systems JWST is finding. But for the deepest, earliest, most extreme objects, the ones that sit furthest outside the boundaries of what our models predict, it may not be enough. And science, when one answer is not enough, does not stop, it reaches for the next one. Imagine a cloud of gas the size of a galaxy. Not a galaxy yet, not even close. Just gas, hydrogen and helium, the same two elements the universe began with, hanging in space in a region where gravity has begun to assert itself, where the slow, patient arithmetic of mass and distance has started to pull things inward. Under normal circumstances, you know what happens next. The cloud fragments. It breaks apart into smaller pieces, each piece collapsing on its own, each one heating as it falls and eventually igniting the hydrogen at the core, reaching temperatures and pressures high enough that atoms begin to fuse. Stars are born. Hundreds of them, thousands. The cloud becomes a stellar nursery. And what eventually forms from it is not a single object but a population. A diverse, distributed collection of burning points spread across light years of space. That is the normal story. That is what gas clouds do. But the early universe was not, in certain critical ways, normal. And in some regions of it, under conditions that theorists have been modeling carefully, for the last 2 decades, the normal story did not happen. The cloud did not fragment. It did not break apart into stars. It fell, all of it, together inward. One piece, one collapse. And what formed at the center of that collapse was not a star. It was a black hole. This is the direct collapse black hole scenario, DCBH, in the abbreviation that appears in the literature. It is, of the 3 theories we are considering, the one that requires the most specific conditions, the one that depends on a particular set of circumstances coming together in the right place at the right time. And it is also the one that, in the opinion of a growing number of theorists, may best explain the most extreme overmassive black holes in the JWST data. The key to understanding why it works and why it only works under specific conditions is the concept of cooling. We touched on this briefly in the last section. In the modern universe, gas clouds cool efficiently because they contain heavy elements, carbon, oxygen, silicon, that radiate energy away in characteristic emission lines as electrons jump between energy levels. That cooling allows the cloud to lose pressure, to contract, to fragment into the smaller pieces that become individual stars. Take away the heavy elements, and cooling becomes much harder. In the very early universe, heavy elements were scarce. The first stars were only just beginning to forge them in their cores. Before those first stars lived and died, and scattered their products into the surrounding medium, the gas was nearly pristine, almost entirely hydrogen and helium. In that pristine gas, cooling was slow. But slow cooling alone is not enough to produce a direct collapse. Hydrogen can still cool through its own emission mechanisms, through the formation of molecular hydrogen, which radiates energy efficiently enough to allow fragmentation even without heavy elements. For a truly monolithic collapse, for the whole cloud to fall inward as a single unit, you need to suppress even that. You need to destroy the molecular hydrogen before it can do its work. And there is a mechanism that can do exactly that. Ultraviolet radiation. If a massive, young galaxy forms near a pristine gas cloud close enough that the ultraviolet light from its newly formed stars bathes the cloud in intense radiation, that radiation can dissociate the molecular hydrogen, break the molecules apart, before they can cool the gas efficiently. Leave the cloud warm, leave it pressure supported against fragmentation, and a warm, unfragmented cloud, falling under its own gravity, does not produce stars, it produces something else. As the gas falls inward, it compresses, it heats, it spins up, it forms a structure sometimes called a supermassive star, sometimes called a quasi-star, depending on the details of the model, that is not quite like anything that exists in the modern universe, an object of perhaps 1 million solar masses, held up not by nuclear burning alone, but by the combined pressure of radiation and rotation, existing in a state of precarious balance for perhaps a few 100,000 years. And then it collapses, not the gentle collapse of a normal star at the end of its life, a total collapse. Collapse that leaves almost nothing behind except a black hole with a mass of perhaps 100,000 solar masses, perhaps 1 million, a heavy seed, far heavier than anything a population star could produce, far heavier than the light seeds of the first theory. Heavy enough that the growth problem, the challenge of reaching 1 billion solar masses in 500 million years, becomes dramatically more tractable. Starting from 100,000 solar masses, instead of 100, you need to grow by a factor of 10,000, not 10 million. The same accretion rates, the same timescales, the same physics, but a much more achievable target. The direct collapse scenario, in this sense, solves the timing problem elegantly. But it creates a different kind of problem. The conditions it requires are specific, almost too specific. You need a massive nearby galaxy producing intense ultraviolet radiation. You need a pristine gas cloud, metal-free, uncontaminated by the products of earlier stellar generations in close proximity. You need the geometry to work out, so that the radiation reaches the cloud efficiently without being absorbed by intervening material. You need the cloud to be massive enough that its self-gravity can overcome its thermal pressure once the molecular cooling is suppressed. All of these conditions have to be met simultaneously in the early universe. With its different density of structures and its pristine chemical composition, such environments may have been more common than they would be today. Theorists have run simulations showing that the necessary conditions could plausibly arise in regions where early galaxy formation was proceeding rapidly, where the first luminous objects were close enough together that their radiation fields overlapped, but plausible is not confirmed. The direct collapse black hole remains, as of now, a theoretical object, something that the physics permits, something that the simulations produce, something that would explain the observations neatly if it exists, but something we have not yet unambiguously detected. The little red dots are candidates. Some of them have the spectral signatures that models predict for direct collapse, objects the emission lines, the compact morphology, the absence of the stellar features you'd expect if the object were dominated by stars rather than an accreting black hole. Some researchers have pointed at specific little red dots and argued that they are, in fact, the first direct observational evidence for the DCBH scenario. Others are not yet convinced. The debate is ongoing. The data is real. The interpretation is contested. That is science. That is what it looks like from the inside, not a clean progression from question to answer, but a messy, productive argument between people who are all looking at the same data and drawing slightly different conclusions. Testing those conclusions against new observations, revising and recalibrating, and slowly, imperfectly, getting closer to something true. There is something worth pausing on here. The direct collapse scenario, if correct, implies something striking about the relationship between galaxies and black holes in the early universe. It implies that the formation of a supermassive black hole seed was not an internal process, not something that happened inside a single collapsing structure in isolation. It was a neighborhood event. It required a nearby galaxy to bathe the gas cloud in radiation. It required proximity, interaction, one structure influencing another across distances of tens of thousands of light years. The first supermassive black holes in this picture were not born alone. They were born in the presence of something else, something that was already luminous, already full of stars, already in its own way a galaxy, which raises a question that the theory doesn't fully answer. If the DCBH scenario requires a nearby galaxy to provide the necessary radiation, then the galaxy came first, at least locally, at least in that neighborhood. The black hole seed formed because the galaxy was already there, already shining, already altering the conditions of the surrounding medium. But then what produced the overmassive black holes that appear to have no galaxy around them? The ones like A2744S01, sitting in the early universe with almost no stellar mass, no assembled structure, no neighborhood galaxy visible nearby. The direct collapse scenario has answers to this question. The galaxy that provided the radiation may have been a temporary neighbor, may have since merged or dispersed, may be hidden behind dust. The argument is not settled, but the question remains open. And open questions in a story like this one are not failures. They are the places where the next discovery will happen. The places where the next theory waits, patient and dark like a black hole at the center of something that has not yet become a galaxy. Let that image rest with you. A place where the next answer lives not yet visible, not yet resolved, but there, massive, inevitable, drawing everything slowly toward it. The third theory is the strangest of the three. It does not ask how black holes formed in the early universe. It asks whether some of them were there from the very beginning, before the first stars, before the first gas clouds, before any of the structures we have been talking about had time to form. Whether some of the darkness we find at the center of galaxies today was woven into the universe at the moment of its birth. There is a version of this story that begins before everything else, before the first stars, before the first gas clouds, before the first atoms had fully cooled from the plasma of the early universe. and settled into the hydrogen and helium that would eventually become the raw material of everything we can see. A version in which the darkness was not produced by the universe as it evolved. A version in which the darkness was there from the start, built into the initial conditions, written into the fabric of space-time at a moment so early, so close to the origin of everything, that the physics describing it sits at the edge of what our current understanding can reach. This is the theory of primordial black holes, and of the three explanations for the overmassive black holes, is finding it is the one that reaches furthest back, the one that requires the least from the universe's subsequent evolution and the most from its very first moments, the one that, if true, would mean that some of the darkness anchoring the largest structures in the cosmos today has been here since nearly the beginning of time itself. To understand how a black hole could form before stars, before galaxies, before atoms, you have to go back to the first fraction of a second after the Big Bang. The universe in those first moments was not smooth. It was dense, beyond imagination. All the energy that now fills 93 billion light-years of observable space, compressed into a region smaller than a proton, and within that density, there were fluctuations. Small variations in the distribution of energy from place to place. Regions that were, by an almost imperceptible margin, slightly denser than their surroundings. In the universe we live in today, those fluctuations grew slowly, over hundreds of millions of years, into the large-scale structure of galaxies and galaxy clusters and the cosmic web. The seeds of that structure were planted in the first moments, and then watered, patiently, by gravity across cosmic time. But in certain models of the early universe, particularly in scenarios involving a period of extremely rapid expansion called inflation, those initial fluctuations were not all small. Some regions of space may have had density fluctuations, large enough that gravity could overcome the outward pressure of the hot dense plasma almost immediately. Not after millions of years of patient accumulation, not after stars had formed and died, and seeded the medium with heavier elements in the first second, or the first millisecond, or earlier still. In those regions, if the density was high enough and the fluctuation was large enough, the collapse would have been direct and total. No stars, no gas clouds, no intermediate structure of any kind. Just a region of space, dense enough that it crossed the threshold, the point at which not even the outward pressure of the most energetic plasma in the history of the universe could arrest the infall. Then in a fraction of a second, a black hole would exist. A primordial black hole, not the remnant of a star, not the product of a gas cloud collapse, not the endpoint of any evolutionary process involving matter in the forms we recognize. A black hole formed directly from the energy density of the very early universe, stamped into space-time at a moment when the cosmos was still finding its shape. The idea is not new. It was first proposed in the early 1970s by Stephen Hawking and Bernard Carr. For decades it sat in the literature as an interesting theoretical possibility, something the physics permitted but for which there was no direct observational evidence. Ghost in the equations, a permitted solution that the universe may or may not have chosen to use. Then JWST started finding black holes that were too massive, too early by every model that assumed they had to grow from stellar seeds. And the ghost became interesting again. Because if primordial black holes formed in the first moments of the universe, if they formed with masses anywhere from a fraction of a gram to millions or billions of solar masses, depending on the size and timing of the density fluctuation that produced them, then the problem of growing a supermassive black hole in 500 million years simply disappears. You don't need to grow it. It was already there. Already massive. Already sitting in the early universe. Already accreting whatever gas happened to fall into its gravitational well. Already seeding the formation of the structure that would eventually become a galaxy around it. It's not a product of the galaxy. Not even a seed in the conventional sense. Something older. Something that predates the entire hierarchy of structure formation that cosmologists spend their careers modeling. The primordial black hole scenario, if correct, inverts the story of cosmic evolution in a profound way. In the conventional picture, the universe builds complexity from simplicity. Simple elements become stars. Stars forge heavier elements. Those elements form planets and dust and gas clouds and eventually galaxies. Complexity accumulates, structure grows. And at each stage, the previous stage is the cause of the next. But primordial black holes break the chain. They are not caused by anything in the subsequent history of the universe. They are initial conditions. They are what the universe started with, not what it produced. And If they are massive enough, if the density fluctuations that created them were large enough, they could have been the gravitational anchors around which everything else assembled, not the products of galaxies. The seeds of them, the attractors around which the first gas clouds fell, the centers around which the first stars formed. The reason that certain regions of the early universe collapsed into structure faster than others, not because of random fluctuations in dark matter density alone, but because there was already something massive there, pulling, already waiting. This picture has a quality to it that is hard to describe scientifically but easy to feel intuitively. It suggests that the darkness we find at the center of every galaxy, including our own, including the Milky Way with Sagittarius A sitting quietly 26,000 light-years from where you are right now, may not be a consequence of all the stars and gas and evolution that surrounds it. It may be the reason for it, the black hole not as product of the galaxy, but as its origin point, its gravitational seed, the thing that was here first in the darkness before stars, drawing matter toward it across distances and timescales that the word patient does not come close to capturing. The evidence for primordial black holes is indirect, as yet, comes from the overmassive systems. JWST is finding objects like A2744 QSO1 that appear to have black holes disproportionately large relative to their stellar mass, which is exactly what you would expect if the black hole formed before the stars and simply had a head start on everything. Recent simulations have shown that massive primordial black holes can reproduce the properties of the most extreme JWST discoveries, the high black hole to stellar mass ratios, the compact morphologies, the presence of active accretion in environments with very little assembled stellar structure. The numbers work, the timing works. What is missing is a direct detection, a way to distinguish a primordial black hole from a very rapidly grown conventional seed in a specific observed system. The signatures overlap. The predictions are similar enough that current data cannot cleanly separate them, but the search is underway. Gravitational wave observatories, including the future space-based LISA mission, expected to launch in the next decade, may be able to detect the mergers of primordial black holes in the early universe. The pattern of those mergers, their masses and frequencies, and the distribution of the gravitational wave signal across the sky would carry fingerprints of primordial origin that conventional seeds would not produce. The next generation of observations may tell us, or the generation after that. Science is often like this. The question outruns the instruments catch up, and in the gap between them, in the space where the answer is not yet known, is where the most interesting thinking happens. What stays with you, sitting here in the quiet of this hour, is not any single theory. It is the shape of the question itself. 3 different answers to where the darkness came from. 3 different versions of what was here first, and in all 3 of them the collapsed massive star, cloud, the direct collapse cloud, the primordial density fluctuation, the black hole arrives before the galaxy is finished, before the stars around it have had time to fully assemble into the structures we recognize. In all 3 versions, the darkness precedes the light, not as metaphor, not as poetry, as physics, as the actual sequence of events in the actual universe we live in, inferred from actual measurements, made by an actual telescope that human beings designed and built and launched and unfolded in the darkness a million miles from home. The darkness came first, and the light, all the stars, all the warmth and complexity that followed came after, around it, because of it, in response to something that was already there, already pulling, already patient, in a way that only things without consciousness can be patient, waiting for the universe to build itself around the fact of their existence. Rest in that for a moment. 2. You don't need to choose between the theories. Neither do the astronomers, not yet. The data will choose eventually. Until then, all 3 possibilities are alive. All 3 versions of the early universe are real, in the sense that physics permits them. All 3 are being tested, refined, argued over in the journals and the conference rooms and the late-night conversations between people who have given their working lives to understanding what was here before we were. What was here before anything was. There is something the 3 theories share that is easy to miss when you are focused on their differences. Each one requires a bridge, a moment of transition, sometimes fast, sometimes slow, sometimes violent, sometimes almost gentle, between the conditions of the very early universe and the supermassive black holes we find anchoring the first galaxies in the JWST data. The light seed theory bridges through stellar death. A massive star collapses and leaves a remnant that grows. The direct collapse scenario bridges through a single, catastrophic infall gas becoming black hole, without the intermediate step of stellar life. The primordial black hole theory requires no bridge at all, which is part of its appeal and part of what makes it hardest to test. But there is another object, one that sits at the intersection of all three theories, that appears in the models and the simulations, and increasingly in the observational data, in ways that researchers are only beginning to fully appreciate. That may be the most important bridge of all. An object so large, so brief, so extreme in its properties that nothing like it exists in the universe today. A supermassive star, not a massive star in the population's sense. Not an object of a few hundred solar masses, enormous by modern standards but still recognizably stellar in its structure and behavior. Something categorically larger than that. Something that pushes against the very boundaries of what physics allows a star to be, before the concept of star breaks down entirely. An object of perhaps 1 million solar masses, held together not primarily by the pressure of nuclear fusion, but by the pressure of radiation itself, the outward push of photons produced in the core, balancing the inward pull of gravity across a volume so vast that the star's outer atmosphere would extend beyond the orbit of Jupiter if you placed it where our sun is. 1 million solar masses, burning, collapsing, existing for perhaps 100,000 years before the end, and then gone not in a supernova in any conventional sense, but in a direct collapse to a black hole, total, complete. 1 million solar masses of hydrogen and helium folding inward in a matter of hours, leaving behind a seed black hole of extraordinary mass. The supermassive star is not new to theory. It has existed in the equations for decades, appearing in certain limiting cases of stellar structure models as a permitted but seemingly exotic solution. An object that physics allows but that astronomers expected never to actually find, because the conditions required to produce it seem too specific, too fragile, too dependent on the pristine chemistry of a universe that no longer exists. But the little red dots changed that expectation. When astronomers began looking carefully at the spectra of little red dots, those compact, ancient, deeply red objects scattered across the early universe, some of them found something unexpected alongside the broad emission lines that suggested active black holes. They found the spectral signatures of something very large, not a black hole directly, not the accretion disk emission you would expect from gas falling onto a supermassive object, something different. An extended photosphere, a stellar atmosphere surrounding the central object. Spectrum that, when compared to models of what a supermassive star would look like from 13 billion light-years away, matched in ways that were difficult to dismiss. One research team, Nandel and Loeb, working with models of population the supermassive stars at around 1 million solar masses, showed that these objects could reproduce the luminosity of the brightest little red dots, that, the shape of their emission, the characteristic Balmer break in their spectra, the hydrogen emission lines, all of it matched what a supermassive star would produce, with a remarkable degree of consistency. Not all little red dots, not even most of them necessarily, but some, a subset, the brightest, most extreme ones, the ones that sit most uncomfortably outside the parameter space of conventional early galaxy models. If those objects are supermassive stars, or systems containing supermassive stars, then the bridge between the early universe and the supermassive black holes, JWST is finding, becomes much clearer. The sequence, in this picture, would look something like this. In the earliest epochs of the universe, the first few 100 million years, certain regions of space contain pristine gas clouds of extraordinary mass, millions of solar masses of hydrogen and helium, cooling slowly, falling inward under their own gravity, unable to fragment efficiently into a normal stellar population. Under the right conditions, the absence of metal coolants, the suppression of molecular hydrogen by nearby radiation, the particular geometry of dark matter halos that concentrated the gas, without dispersing it, the infall produced not a cluster of stars, but a single, unified object, a supermassive star, briefly luminous beyond almost anything else in the universe at that time, radiating at rates that would make the most energetic quasars today seem modest. Burning through its fuel, if burning is even the right word for the complex, radiation-dominated processes happening in a stellar core at that scale, in a geological eye blink, and then collapsing, directly and completely to a black hole. The resulting seed would be, depending on the details of the collapse and how much mass was lost during the star's brief life, somewhere between 100,000 and 1 million solar masses, far heavier than any stellar remnant in the modern universe, heavy enough to reach 1 billion solar masses by 600 million years after the Big Bang, with accretion rates that are unusual but not physically implausible. Heavy enough to explain the most extreme objects in the JWST catalog without requiring continuous super Eddington growth. The supermassive star scenario sits comfortably between the first two theories we discussed. It is more extreme than the light seed scenario. The seed it produces is orders of magnitude more massive than the remnant of even the largest population star, but it requires a real stellar object as an intermediate step. Unlike the pure direct collapse picture, where gas becomes black hole with no stellar phase at all, in some models they blur together. The distinction between a very massive direct collapse and a supermassive star that immediately collapses is partly definitional, a matter of timescale and degree, rather than a sharp categorical boundary. The physics lives on a spectrum. What matters for our purposes tonight is not the exact boundary between theories. What matters is the image, 1 million solar masses of gas, somewhere in the early universe, pulled together by gravity into a single coherent object, burning briefly with a light so intense that it would have been visible across the entire observable universe had there been anyone to see it. And then, in a moment of total gravitational surrender, becoming something else, something that does not burn, something that does not radiate by the familiar mechanism of nuclear fusion, something that takes in whatever falls toward it and gives back only the energy of accretion and the distortion of space-time in its immediate vicinity, a black hole. Already millions of solar masses, already waiting, already beginning the long, slow work of drawing matter toward it, gas, dust, eventually stars, eventually the full assembled structure of a galaxy across the billions of years that separate that moment from this one. There is a particular quality to imagining this object, not a star in any sense you would recognize, not a planet, not a galaxy, something that existed in a universe so young it barely had a temperature yet, in a form that no longer occurs anywhere we can observe, for a time so brief that the entire lifespan of a supermassive star would pass in less time than it took the first modern humans to develop language. Flash. And then darkness. And then everything that followed from that darkness, the gas that fell in, the stars that formed around it, the galaxy that assembled itself over hundreds of millions of years, the subsequent generations of stars that lived and died and produced the carbon and oxygen and iron that eventually found their way into planets and across an almost incomprehensible chain of causation into you, into the body lying here in the quiet of this particular hour, into the atoms that are reading these words in the slow, patient language of breath and heartbeat. There is something in that chain worth sitting with, the supermassive star. If it existed, and the data suggests that something like it did, in some form, in some of the earliest and most extreme objects the universe produced, was not a footnote to the story of cosmic evolution. It may have been one of the first sentences, a single, massive, brief burning that ended in darkness and produced, from that darkness, the seed of everything that grew around it. Stars don't usually work like that. They burn and they scatter, they explode and they spread. They seed the universe with complexity and leave behind remnants that are modest. By cosmic standards, neutron stars the size of a city, black holes a few dozen solar masses at most. The supermassive star did not scatter. It did not spread. It collapsed into itself entirely and kept everything and waited. And what grew around it slowly, across time, was not scattered light. It was a galaxy. Which brings us at last to the question that all three theories are really answering. Not just how the black holes formed, not just what mechanism produced the seed, or grew it to its extraordinary mass, or placed it in the early universe before most of the stars existed, but what this means. For galaxies, for structure, for the long chain of causation that connects a density fluctuation in the first fraction of a second after the Big Bang to the world you are lying in right now. For the question of whether the darkness at the center of things is an ending or a beginning. Whether the void is where everything concludes or where everything starts. We have spent a long time in the dark tonight, in the cold mathematics of the early universe, in the spectra of objects so distant that the light reaching us left them before our solar system existed, before the Earth existed, before the sun had ignited, in the careful, contested, ongoing argument between theorists and observers about what was here first and how it grew and what the sequence of events actually was in the first billion years of cosmic time. It is worth stepping back now, not away from the science, but far enough back to see the full shape of what we have been looking at, because the question of whether black holes preceded galaxies is not, In the end, just a question about black holes. It is a question about causation, about what drives what, about the direction in which the universe builds complexity, whether it moves from the simple to the complex in a smooth, orderly progression, each stage following from the last in a chain we can trace cleanly back to the beginning, or whether it is stranger than that, whether the very first structures were not the smallest and simplest things but something else entirely, something massive and dark and fundamental, around which everything else, all the light, all the stars, all the long, slow elaboration of matter into complexity, assembled itself in response. Consider what it would mean if the primordial black hole theory is correct. If some of the supermassive black holes anchoring the largest galaxies in the observable universe formed in the first second, the first millisecond after the Big Bang, from density fluctuations in the primordial plasma, then they predate everything. They predate the first atoms, which formed 380,000 years after the Big Bang, when the universe cooled enough for electrons to bind to nuclei. They predate the cosmic microwave background, that faint afterglow of the Big Bang that we can still detect in every direction, the oldest light in the universe. They predate the first stars by hundreds of millions of years. They would be the oldest discrete objects in existence, older than light in any meaningful sense, and the galaxies that formed around them, the Milky Way, Andromeda. The vast population of galaxies we observe, stretching to the edge of the visible universe, would not be independent structures that happen to accumulate a black hole at their centers as a byproduct of stellar evolution. They would be the aftermath, the accumulated response of gas and dark matter and stellar populations to a gravitational presence that was already there, already massive, already shaping the flow of matter across distances of hundreds of thousands of light years before a single star had formed. In this picture, the galaxy is not the primary structure. The black hole is. The galaxy is what grows around it, what falls toward it, what organizes itself in the long gravitational conversation between the black hole's mass and the surrounding medium. Stars form in the regions where gas density reaches the threshold for collapse, regions shaped by the black hole's influence. They live and die and enrich the medium with heavier elements. Then those elements allow the next generation of stars to form more easily. And the process cascades across hundreds of millions of years into the elaborate, multi-generational stellar ecosystem we observe in mature galaxies today. All of it downstream. All of it, in some sense, a consequence of the darkness that was already there. Now consider what this means for our own galaxy. At the center of the Milky Way, 26,000 light-years from where you are lying right now, sits Sagittarius of 4 million solar masses. Quiet, currently not actively accreting in any significant way, not producing the jets of energy that active galactic nuclei produce, just sitting there in the relative stillness of a mature galaxy that has largely finished its most intense period of star formation. We have known about Sagittarius A for decades. We have watched stars orbit it at extraordinary speeds, the evidence from which its mass was inferred. We have now even imaged it directly, using a network of radio telescopes spread across the entire planet. The Event Horizon Telescope, producing an image of its shadow against the glowing gas around it. We know it is there. What we do not know, what no one yet knows with certainty, is whether Sagittarius A is a product of the Milky Way or its seed, whether the hundreds of billions of stars in our galaxy, including our Sun, formed because of processes that were already underway independent of the central black hole, or whether the black hole was there first, in some earlier form, as a gravitational anchor around which the protogalactic gas began to fall, triggering the conditions that allowed the Milky Way to assemble itself. Whether we are, in some deep sense, downstream of that darkness. The atoms in your body were forged in stars, that much is certain. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all of it was produced in stellar cores and scattered into the interstellar medium by stellar deaths, and eventually found its way into the molecular cloud that collapsed to form our solar system about 4.6 billion years ago. You are made of stars. That is not a metaphor, it is chemistry. But the stars themselves, the stars that made you, formed in a galaxy, and that galaxy may have formed around something much older than any of its stars. Something that was present in some form before the first generation of stellar furnaces had ignited. Something that shaped the conditions under which those furnaces could ignite at all. The black hole came first. Then the chain of causation runs differently than we thought. Not Big Bang, hydrogen, stars, black holes, galaxies, us, but something closer to Big Bang black holes, galaxies, stars, us. The darkness earlier in the sequence, the light a consequence of it. That reordering is not trivial. It changes the story of what we are and where we came from in ways that are subtle but profound. Tell me, it places the most extreme objects in the universe, the most gravitationally powerful, the most mysterious, the least understood, not at the end of the chain of cosmic evolution, but at the beginning of it. Not endpoints, origin points, not the places where matter goes to disappear, the places where structure began. There is another implication worth sitting with. If black holes shaped the formation of galaxies, if their gravity influenced where and when stars formed, if their feedback regulated the growth of the stellar populations around them, then the properties of the galaxy you live in are not independent of the properties of the black hole at its center, the size of the Milky Way, the distribution of its spiral arms, the rate at which it formed stars across its history, the particular chemical composition of the molecular cloud that gave rise to our solar system. The fact that our sun formed with exactly the right amount of heavy elements to allow the formation of rocky planets. The fact that one of those rocky planets ended up at exactly the right distance from the sun to allow liquid water on its surface. None of those things were inevitable. All of them depended on the history of the galaxy they occurred in, and the history of the galaxy depended, in ways we are only beginning to understand, on the black hole at its center. Trace it back far enough past the molecular cloud, past the earlier generations of stars, past the assembly of the Milky Way itself, and you arrive, eventually, at the question of what seeded that galaxy. What provided the initial gravitational anchor around which the proto-galactic gas began to fall? Whether that seed was a direct collapse event a few 100 million years after the Big Bang, whether it was the remnant of an enormous population Phi star, whether it was a primordial black hole formed in the universe's first second, you cannot answer that question from here. Not tonight, not yet, but you can feel the weight of it. The possibility that the darkness at the center of our galaxy is not an accident, not a byproduct, but something closer to a prerequisite of something that had to be there in some form for the galaxy to have formed the way it did, for the stars to have formed the way they did, for the molecular cloud to have collapsed the way it did, or the sun to have ignited, and the earth to have formed, and water to have pooled on its surface, and life to have emerged from that water, and that life to have eventually produced creatures capable of building telescopes and pointing them at the early universe and asking, in the careful language of physics and mathematics, what was here before us? The answer, it seems, may be, the darkness was. Let that settle, not as something frightening, not as something that diminishes the light, the stars, the warmth, the extraordinary improbability of everything that followed, but as context, as the full shape of the story. A universe that began not in light but in something else, something denser and stranger and harder to see, something that did not radiate or burn, but simply pulled steadily, patiently, for billions of years, until the light came to it, until the gas fell in, and the stars formed, and the galaxies assembled themselves around the fact of its existence. And then the light stayed. And everything that has happened since has happened in the light, including this, including you, here, in the particular quiet of this particular hour, at the far end of a chain of causes that reaches back to something we are only now beginning to see. The James Webb Space Telescope is still up there. Right now, as you lie here, as your breathing slows and the room settles into the particular stillness of deep night, it is still working, still collecting light, still turning its golden mirrors toward patches of sky that no instrument has ever examined at this depth, at this sensitivity, in this wavelength range. It does not sleep. It does not pause to consider what it has found. It does not feel the weight of the implications. It simply gathers light, photon by photon, and sends the data home across 1,000,000 miles of space to the teams of people who will spend months and years making sense of it. That is the nature of telescopes. They look, we interpret. And right now, the interpretation is incomplete. That is not a failure. It is the current state of a genuine scientific revolution, the kind that does not announce itself cleanly, that does not arrive with a single decisive observation and a tidy explanatory framework ready to replace the old one, the kind that arrives as an accumulation, as a pattern that keeps emerging from data that was supposed to confirm what we already believed, and instead keeps suggesting something else, something older, something darker, something that was here before we thought anything like it could be. We do not know, with certainty, whether black holes came before galaxies. We have strong evidence that some black holes in the early universe were far more massive than any conventional growth model can easily explain. We have objects real, confirmed, have spectroscopically verified objects that appeared to have black holes disproportionate to their stellar mass in ways that suggest the black hole was not produced by the stars around it, but preceded them. We have 3 serious theoretical frameworks, each one capable of explaining some of the observations, none of them yet proven to be the single correct answer. We have a question that the data keeps sharpening, and we have a telescope that is not finished looking. In the years ahead, we'll continue to find objects in the early universe that push the boundaries of our models. It will confirm more little red dots, to measure more black hole masses, probe the spectra of more compact early galaxies with the precision needed to distinguish between the competing theories. It will look further back toward redshifts of 15, 20, 25, toward a time when the universe was only 100 million years old, or less. What it finds there, no one knows. The models make predictions. Some of them predict that even at those extreme redshifts, there will be luminous objects, sources of light, that should not yet exist by any standard accounting of how quickly structure can form. Some of those predictions come from the primordial black hole models, which suggest that the seeds of the largest structures were laid down so early that even the deepest JWST observations may be catching only the downstream consequences, not the origin itself. Other predictions come from the direct collapse models and the supermassive star scenarios, objects that would be extraordinarily luminous for their brief existence. And that might leave detectable signatures in the spectra of the systems that formed around them. The next generation of instruments will push further still. The extremely large telescope, currently under construction in the Chilean desert, will be able to take spectra of individual stars and galaxies at significant redshift, opening a window on the chemical composition of the earliest stellar populations that is currently closed to us. The Nancy Grace Roman Space Telescope will survey vastly larger areas of sky than JWST can cover, potentially finding the rare, extreme objects that tell us the most about the early universe, simply by virtue of existing where our models say they shouldn't. And LISA, the Laser Interferometer Space Antenna, a gravitational wave detector to be placed in space in the coming decade, may be the most decisive instrument of all, because if primordial black holes exist, and if they merged in the early universe, those mergers produced gravitational waves, ripples in spacetime that have been propagating outward ever since, waves that carry, encoded in their frequency and amplitude and timing, the fingerprint of their origin, the mass of the objects that merged, the epoch in which the merger occurred, whether the black holes were primordial or conventional. LISA will listen for those waves, and if they are there, if the early universe produced a population of primordial black hole mergers that left their signature in the gravitational wave background, we will hear them. We will have, for the first time, direct evidence not just that overmassive black holes existed early, but that some of them were there from nearly the very beginning. The beginning, that word carries a particular weight. Tonight we use it casually. The beginning of the universe, the beginning of time, the Big Bang is the starting point of everything. But what JWST is teaching us, or slowly and through accumulation, is that the beginning was not empty in the way we imagined. It was not a blank slate on which structure gradually wrote itself. It may have contained, from its very first moments, the seeds of the largest and most persistent structures in the cosmos. And not as a plan the universe does not plan, but as a consequence of the physics of extreme density and extreme temperature, and the particular way that energy distributed itself in those first instants. The darkness was early, perhaps primordially early, and everything that has happened since the hydrogen, the first stars, the supernovae, the heavy elements, the next generation of stars, the molecular clouds, the planetary systems, the long, improbable chain of chemistry and biology that eventually produced creatures who could look up at the night sky and wonder what they were looking at. All of it happened in the gravitational shadow of something that was already there. That is not a diminishment of any of it. If anything, it deepens the strangeness, the improbability, the specific, contingent, unrepeatable character of the universe we find ourselves in, because the darkness did not determine the details. It shaped the large-scale conditions. It provided the gravitational scaffolding. But the particular stars that formed, the particular supernovae that scattered their contents, the particular molecular cloud that collapsed to produce our sun and its planets, all of that was downstream of the large-scale structure, not dictated by it. The black hole at the center of the Milky Way may have been a necessary condition for the Milky Way to exist at all, but it did not cause the sun. It did not cause the Earth. It did not cause you. Those required everything that came after. All the stellar generations, all the chemistry, all the time, 13.8 billion years of time, at the end of which, here you are, in a body made of atoms forged in stars that formed in a galaxy that may have assembled itself around a darkness older than any of its light, lying in the quiet of a night that is itself a small, local, temporary stillness, in a universe that is anything but still, that is expanding, in every direction, at every moment, carrying its billions of galaxies further from each other, across distances that grow with every second. You will not solve the question of what came first tonight. Nobody will. The data is still coming in. The models are still being revised. The papers are still being written and debated and revised again. The telescopes are still looking. This is science, as it actually is not a completed edifice of settled knowledge, but a living process. A conversation between observation and theory that has been ongoing for as long as humans have looked at the sky and wondered. And that will continue long after this particular night has passed, and the particular question of black holes and galaxies has been answered, and replaced by whatever stranger question its answer opens up, because that is how it always works. Every answer is a door. On the other side of every resolved mystery is a deeper mystery that the resolution reveals. The question of what came first, the galaxy or the black hole, has been opened by JWST into 3 other questions, each one more fundamental than the last. What seeded the first black holes? What were the conditions of the very first fraction of a second? What does the distribution of primordial density fluctuations tell us about the physics of inflation? About what happened before the Big Bang? About the nature of the universe, at energies we cannot recreate in any laboratory on Earth? These questions are waiting, patiently in the dark, the way black holes wait, for the instruments to improve, for the theories to sharpen, for the next generation of people who will spend their working lives trying to understand what the universe is, and where it came from, and why it is the way it is, rather than some other way. They are out there somewhere, those people. Some of them are children right now, lying in rooms not so different from the one you are in, looking at the dark ceiling and feeling, without quite having the words for it yet, the pull of very large questions, the sense that the universe is stranger and more interesting than anything they have been told so far. They will build the instruments that answer what JWST has opened. They will look where we have not yet looked, and they will find almost certainly something that none of the current theories predicted, something that requires another revision, another expansion of the framework, another night like this one, quiet, late, full of the particular quality of attention that comes when you stop trying to manage your understanding of the universe and simply let its strangeness move through you. That is what tonight has been. Not an explanation, not a resolution, an opening. The universe is very old and very large and almost entirely dark. The light, all of it, every star that has ever burned, every photon that has ever traveled across the void between galaxies, is a small fraction of what exists. Most of what the universe contains does not shine, does not radiate, does not announce itself to instruments designed to collect light, simply pulls. And in that pulling, in that patient, constant, ancient gravitational conversation between mass and space and time, the structure of everything we can see has been slowly, imperfectly, extraordinarily assembled, including the world outside your window, including the air moving quietly in and out of your body right now, including this moment late, still, at the edge of sleep, which is itself a small event in a very large universe that has been building toward complexity for nearly 14 billion years and shows as yet no sign of being finished. Let it be unfinished. Let the question remain open. The darkness that was here before the stars is the same darkness that is outside your window, tonight, older now, thinner now, stretched across 93 billion light-years of expanding space, but continuous with what it was, still here, still pulling, still in its patient and ancient way, making room for whatever comes next. Rest now. The universe will keep doing what it does, it always has.